In the last video, I talked about interpreting a multiple linear regression model, and I'm going to finish up this chapter by talking about how to use that model to either estimate an expected value of y or predict an individual value of y. So let's focus first on estimating the expected value of y at a particular set of values for the predictors x1 up to xk. So our formula in very simple terms is y hat, so the predicted value of y at those particular values of x1 up to xk, plus or minus a t percentile times the standard error of estimation. So that's the very basic formula. There's details here which I'm not going to dwell on about the t percentile and the standard error of estimation. The reason I'm not going to dwell on those is because we're going to use statistical software to get this interval, and we're going to focus more on interpretation. A couple of things to note though before we do that is, so a confidence interval will be narrower when we've got a large sample size, when the particular values of x that we're predicting at are close to their sample means, when the regression standard error s is small, and for lower levels of confidence. So all else being equal, a 90% confidence interval is narrower than a 95% confidence interval. So the example that we'll work with is our shipping example again. And so if I go back to R, so our model, remember, just has two predictors in it, total weight shipped and average shipment weight. And I'm interested in estimating the population mean, expected value of y, expected labor hours for total weight shipped of 6 units and average shipment weight of 20 units. And so if I use this function predict, and if I specify that the interval is going to be a confidence interval, then that's going to give me that confidence interval for the population mean. So it tells me what y hat is, the fitted value. So that would be the value you get if you plug in TWS equals 6 and ASW equal 20 into the regression equation, the estimated regression equation, which remember was given by these numbers here in the coefficients table. So that gives me my y hat, and then y hat minus a t percentile times the standard error of estimation is equal to 95.4, and y hat plus that t percentile times the standard error of estimation comes to 105.03, or 105.0 to one decimal place. So how do we interpret that? So we can say something like we're 95% confident that expected weekly labor hours is between 95.4 and 105.0 when the total weight shipped is 6,000 pounds and average shipment weight is 20 pounds. If we want to get a little more technical, we can get into repeated samples, but for practical purposes, this is a good way of summarizing what that interval represents. What about a prediction interval for an individual y value? Okay, so here we're not estimating a population mean. Instead, we're predicting an individual y value. So in our shipping context, we're not thinking about what the average labor hours is or are for TWS equals 6 and ASW equal 20. We're thinking about, well, if TWS equals 6 and ASW equals 20, what are the actual labor hours predicted to be? So that's a harder question to answer. There's more uncertainty in a prediction than there is in estimating a population mean. Otherwise, everything looks very similar. Okay, our formula kind of has a very similar format. So it's centered at y hat, so our fitted value, and I've just put a star on here just to denote that we're predicting an individual value rather than estimating a population mean. And then we've got plus minus t percentile again. That t percentile will be the same as in the confidence interval. And now we've got a standard error of prediction rather than a standard error of estimation. And the standard error of prediction is always a bigger number than the standard error of estimation. And so this prediction interval is always wider than the corresponding confidence interval for the mean. Same factors influence how narrow or how wide that interval is, though. So the interval tends to be narrower for large samples. X is close to their sample means. Situations where the regression standard error is small, and for lower levels of confidence. And as I mentioned, since the standard error of prediction is larger than the standard error of estimation, the prediction interval is always wider than the corresponding confidence interval. So let's go back to R and get the prediction interval. So use the same function predict, only now we change the argument interval to read prediction instead of confidence. And now same fitted value, of course, but now our lower bound is 81.0 to 1 decimal place. Let's do my rounding correctly, up to 119.4. How to interpret that? Well, we can say something like we're 95% confident that actual labor hours in a week is between 81.0 and 119.4 when total weight shipped is 6,000 pounds and average shipment weight is 20 pounds. Okay, so probably the most important thing here is the distinction between this prediction interval and the confidence interval for the population mean. So here we're saying that when total weight shipped is 6,000 pounds and average shipment weight is 20 pounds, then when we're predicting the actual labor hours, we can narrow that down to between 81 and 119.4. So imagine that we're actually predicting, say, an individual week in the future where this is going to be how much we're shipping, and the average shipment weight is 20 pounds. Okay, so for that specific week, this is what we're narrowing down the labor hours to be. Whereas for the confidence interval, we're saying that if we think about hypothetical situations in the future where total weight shipped was 6,000 pounds and average shipment weight was 20 pounds, for all those times in the future where this is the case, what is the average weekly labor hours for all those times? Well, then we can narrow it down to a much narrower interval, because on average those weekly labor hours, we expect them to be between 95.4 and 105.0 on average. So that brings us to the end of this chapter now. So we've gone through all the different aspects of multiple linear regression analysis in straightforward cases. So what we'll go on to talk about in the next two chapters is situations which go beyond what we've talked about so far. So we'll talk about things like categorical predictors. We'll talk about model building in a little more detail. We'll talk about influential points. We'll talk about other regression pitfalls, things that can go wrong that we need to look out for. So those will be coming up in the next series of videos on chapters 4 and 5.